Ma'am, we can go now.
Joshita ma'am, are you ready? We can start. Good evening, everyone. On behalf of IEEE Sensor Council and IEEE Sensors Council Hyderabad chapter, Anna University, I welcome you all for today's hands-on session that is being organized under the new initiative plan started under Sensors Council IEEE MEMS training program. Today, we will be having a session on usage of COMSOL and with the complete hands-on. So we have our speaker with us. Let me introduce her. She is Dr. Joshita C. She is a dedicated researcher and academic professional with expertise in electrothermal MEMS actuators, biomedical instrumentation and nanotechnology, and MEMS device design. With a PhD in engineering from SSN College of Engineering, Chennai, her research emphasizes on low power MEMS switches and advanced materials for biomedical applications. She has a strong academic background. Her key achievements includes she has authored 20 plus peer-reviewed publications in journals and conferences on MEMS devices, nanomaterials, and IoT systems. She holds patents on novel bistable switching mechanisms and insulin delivery systems. She has secured national and international funding for projects including research on nanomaterials and diabetes monitoring systems. So we are happy and honored to have you here. I'm audible, right, Joshita ma'am?
Sangeeta ma'am, you are
Hello.
audible.
Yes. So,
Hello.
Joshita ma'am, now the stage is yours. I request Joshita ma'am to share screen and continue her session on the hands-on sessions. Joshita ma'am?
Okay, I think ma'am is
She
facing some
lost
technical issues. Yeah.
Yes,
So
yes. Let's wait for her. Meanwhile, participants, I have shared a software download link.
Hello.
Yes, ma'am. Joshita ma'am, you are audible.
Hello, ma'am. Am I audible?
Yes, you are audible.
Yes, ma'am, you are audible.
Ma'am, you can share your screen and start your session. Joshita ma'am is unable to hear, it seems, but you are audible, ma'am. Yeah, please share your screen and start.
Good evening, all of you. I hope I am audible to all.
Yes, ma'am, you are audible.
Actually, I'm not hearing anything back, so I'm just a little bit confused.
What might be the problem, Priyank, here?
Ma'am, there is some issue from their side.
Okay. If she rejoins, will it solve? We don't know.
Yes, ma'am, we have to check that because
Yeah.
seems like
Okay, I think
there.
I'm audible to all. So I'll
Yeah.
start my session.
Yes.
Good evening, all of you. I'm here to present a training session on hands-on electrothermal actuator. So for this, we will be using a COMSOL multiphysics tool. So let us see what are the things we are going to cover here. So first, I will introduce you to a few set of simulation tools. Then from the various simulation tools, we will be seeing one specific tool called COMSOL multiphysics tool. The software link for the same ma'am already shared in the group. Those who didn't install the software tool can follow the steps which is mentioned in the document. You can directly download and install it. Then today's training is especially on the electrothermal actuator. So I will be showing what is an electrothermal actuator. Already we have seen the theoretical concept and some explanation about the electrothermal actuator by Prida ma'am in the previous session. So here we will see the practical session, like how we can design an electrothermal actuator using COMSOL tool. Then step by step, we will be seeing the implementation process, and finally we will verify the results and how to analyze the electrothermal actuator simulation. So as I mentioned, there are various tools available for the simulation of the MEMS devices. The first one is COMSOL multiphysics. Compared to others, nowadays majority of the MEMS researchers are using COMSOL multiphysics as one of the tool. Here, the main concept is that multiphysics is the main advantage of this one. So whatever may be our MEMS device background, we will be able to incorporate different types of physics to that. So it can be electrothermal actuator or electrostatic actuator, or some kind of sensors, microfluidics, like that. In any kind of physics can be incorporated along with the COMSOL multiphysics. So that is one of the major tool nowadays we are using in MEMS device design. Another one is the IntelliSuite. What is the major difference from COMSOL multiphysics and IntelliSuite? Basically, we can say that in COMSOL, we will be able to do any kind of simulation part. But coming to the fabrication process, the COMSOL directly will not give any fabrication process steps. But in IntelliSuite, both at a time it is possible. We can do the device simulation more or less in a real-time scenario. It will be giving you the results of the simulation, and also it will help you to come up with the process modeling. Like now we are going to fabricate our device with the soy mumps process. So we can choose the process flow, and according to our requirement, we will be defining each step in that, and we can verify the fabrication process also. Okay, so that is the another advantage of IntelliSuite. So both simulation as well as fabrication process can be achieved through this IntelliSuite software tool. Then some of the other simulation tools like ANSYS, Covendaware, etc. also there. They also support MEMS device design. Okay, so that is a few set of simulation tool available in the current scenario. Now, as I mentioned in our presentation, we will be explaining much about the COMSOL multiphysics tool. So what we are telling is that why we are going for COMSOL multiphysics. Okay, so I mentioned that there are multiple physics models are available. So it will be helpful for the researcher or the designer to choose what kind of physics is required, and that can be taken accordingly. And another thing is that the graphical user interface which it is having. Okay, so it will be more helpful uh, when we are seeing the result in from the simulation tool as we expected. Okay, so another thing is that, excuse me once. Okay, in the same design, we can incorporate multiple physics. So that is one another advantage of this COMSOL multiphysics. And whatever may be the device structure or device design, we can incorporate all kind of design into this COMSOL multiphysics. And we can analyze the result, and if any kind of documentation required or any Excel sheet incorporation required, all these things are available in the COMSOL multiphysics. And many platforms are there. There it will explain more about the various simulation tutorials, and if any simulation doubts are there, there are so many communities to discuss about the COMSOL multiphysics doubts kind of thing. So these are about the COMSOL multiphysics. Now let us start with our actual content, that is electrothermal actuator. So from the beginning of the session, multiple classes we have undergone. So in the first class, mm, Suresh Krishna sir also mentioned about the electrothermal actuators, where various electrothermal actuators are discussed. Then Prida ma'am also mentioned about the electrothermal actuator. So here, my research area also electrothermal actuator. So I'm going to explain about the electrothermal actuator. So what is the main advantage of using electrothermal actuator means it can generate comparatively better displacement, output as a displacement due to its thermal expansion amplification. Okay, that's the main advantage of choosing electrothermal actuator. So even when we are giving a small voltage deflection also, based on that, some corresponding thermal expansion will be happening in the device as an output movement. So that output movement or output displacement can be utilized for some other actuations. Okay, it can be used as a valve, it can be used as a switch. Okay, that movement of the output device or output displacement can be taken. So the main working principle of the electrothermal actuator is nothing but the Joule heating and thermal expansion. The physics behind the electrothermal actuator is nothing but the Joule heating and thermal expansion. What is Joule heating and thermal expansion means? Due to the potential difference across the device, there will be a current flow through the device. Okay, so that when there is a current flow through a material, obviously there will be a thermal expansion. Okay, so that thermal expansion will be treated as the output displacement. Okay, here with the picture I can demonstrate that. Here the blue structure, okay, which is the actual design, which is in the normal state. Okay, so it is showing in a inverted V shape. So we can call it as a V-beam actuator. Okay, so when it is in the normal state, no potentials are applied, so there is no thermal expansion, and it has two fixed anchors, and one of the anchor will be act as a voltage node, another anchor will be act as a ground node. Okay, so when we are applying a potential between these two nodes, there will be a current flow through the beam. Due to the current flow of that, there will be a thermal expansion. In which direction it is inclined, towards that inclined direction, there will be the actuation. Since it is angled in upward, so thermal expansion will be happening in the upward direction. So this highlighted yellow color shows the excited state of the thermal actuator. So due to the potential difference, the current flow happens, and due to the current flow, thermal expansion of the device happens. Okay, so the working principle is Joule heating and thermal expansion physics. That is explained through this equations. Okay. There are different types of thermal actuators. The first one is the symmetric actuator, which I shown here as a V-beam actuator. Why it is called symmetric actuator means from the center point, both sides are mirror image. Okay, or both sides are same as the each side. Okay, so we can say that symmetry is there with respect to the origin. So we can say that this is a symmetric actuator. That is one type of a electrothermal actuator. Another one is the asymmetric actuator. What is asymmetric actuator means? There will be some the actual symmetry won't be there with respect to the geometry. Okay, so there are different types of asymmetric actuators are there. One is U-beam actuator. We will be discussing in this session about both V-beam actuator as well as the U-beam actuator. So the U-beam actuator or the asymmetric actuator, we can call it as hot and cold arm actuator or heat switcher. Like that, different names can be given. Why it is called cold and hot arm actuator, I will explain in the upcoming slide. Okay, and the last one is the bimorph type. Okay, so the main difference from the previous one to here is that here different types of material will be coated over the device. That material will be having of different CT, coefficient of thermal expansion. Okay, so due to the change in CTE, the thermal expansion happening in each part of the device will be different. Accordingly, the sometimes we may even expect the out of plane thermal expansion, or some particular direction thermal expansion can be expected. So these are the major types of thermal actuators which can be implemented under electrothermal actuator category. Coming to the V-beam actuator, as I already mentioned, it is a example of a symmetric actuator where with respect to the origin, both the side are equal. Okay, so it is having, it can be with the multiple beams. Okay, here I have used only 2 beams. So depends upon our requirement, we can have multiple beams and all. So parallel to each other. So one side is having a voltage node, another side will be having a ground node. Both the nodes will be fixed properly. And the center part, this beam part will be a suspended structure. Okay, only the anchors are fixed. Remaining all part will be like a under a trench, it will be suspended. So then only it will have the free movement upon the actuation. So this kind of actuations we'll be expecting. Okay, this one we can visualize in our simulation when we apply the respective potential across the voltage node and ground node. There will be a thermal expansion in this direction. So in the V-beam actuator, we will be getting the thermal expansion based on the inclination which we are designing in the structure. So these are some device which fabricated already. So this device which I fabricated during my PhD work. Okay, I fabricated this at Sense IC Bangalore as a INUP participant. So this is the same image of the device fabricated there. So here actually I designed one bistable switch. Okay, so there I have used a pair of V-beam actuators, and central one is a curved beam. Okay, curved beam will have a buckling property when a specific amount of force is applied at the center tip. Okay, so when the V-beam actuator is getting actuated towards this direction, downward direction, then the center curved beam will have a buckling force here, and it will get buckled to the opposite direction. Okay, so based on that, we have developed one bistable switch. Okay, so it is having two stable state, either buckled to the upper side or buckled to the lower side. Like that, it implemented a bistable switch property here. So that is an application of a V-beam electrothermal actuator. Now coming to the asymmetric actuator, one major example is the U-beam actuator or hot and cold beam actuator, which we named earlier. So here from the structure itself, you can understand that it is a like this sideways, it is a U-beam shape is there. Okay, it's a sideways U shape is there. That's why we call it as a U-beam actuator. And one beam or one arm is very thin and another arm is very thick. As per the structural concept, it is mentioned like that. So the as per the principle, we know that where the thickness is less, that beam will get heated up comparatively faster to the thick beam. So that thin beam we can name it as hot beam. The opposite beam or the thicker beam we can call it as cold beam. So when we are applying the voltage across the two fixed anchors, here also the anchors are fixed. Remaining the beam part is a suspended structure. Okay, so when there is a current flow through this hot beam will have the comparatively better thermal expansion with respect to this cold beam. So this will have the bending. Okay, so the hot beam will try to bend downwards and it will be pushing the cold beam also downwards. So if we are arranging in this way, the tip movement will be downward. So like this in the simulation structure, you can see that there is a very thin beam is there, bottom beam is very thick. So when the potential is applied across these two nodes, okay, so the tip will get moved downwards. Same way if we arrange it in the opposite way, if the hot beam is downward and the cold beam is upward, so then we will be getting a upward direction. Okay, so like this combination of this U beam and all, we can design, and this kind of structures can be used for some kind of micro gripper and all. Okay, so these things are very common. here is one same image of a micro mirror. It is a combination of multiple U-beam actuators. You can see that different U-beams are used here. Okay, so the movement of those combinations will give you the mirror to be deflected in different directions. Okay, and this is a same image of a bimorph actuator. Bimorph I already told. Different materials will be used. The difference will be based on the coefficient of thermal expansion. So with respect to that also, we'll be getting some different kind of fluctuations. So that is an example of U-beam actuator. Now we will proceed with the demonstration how we can design one basic electrothermal actuator in the software tool. Okay, so for this purpose, I have prepared one handout. So in that particular handout, the step-by-step process of simulation steps are mentioned. So I think that will be shared with the participants soon. Okay, and for the participant, those who didn't uh, install the software, especially the COMSOL multiphysics 6.2 version software, I shared with the group with the help of ma'am. So that one also can be utilized. Okay, so those who want to do in parallel can get the software and install the software. So one by one step I will explain, and accordingly we can proceed. If someone can respond, like whether I can proceed with the software or not, please. In the chat box, please mention. Or if any other further discussion on the electrothermal actuator working is required, means I can explain that also. Or we will directly proceed with the simulation tool. Okay, it is downloading. So for some people, it will be taking time, depends upon the network capacity. So I thought software will be available with all the person. That's why I just shared now.
You can slowly
Okay.
start,
We will
madam.
proceed with the simulation.
Proceed.
So anyway, handout also shared in the group, I think. So you can later also you can verify the steps and follow the same. Okay. So once we install the software, we'll be getting the, like, I'll show you. We'll be getting a icon like this, COMSOL multiphysics 6.2 in your desktop. Okay, so double click on that and open the software. Okay, so directly it will open. So the first screen which you will be seeing will be like this. I hope it is visible. Okay, so once the software is open, you will be getting an option like this, a new model wizard or blank model. Okay, you can click on the model wizard. So parallelly, if needed, I can show the steps which is shared in the document. 1 second. So this is the handout which I shared in the group. So a brief introduction to the electrothermal actuator is mentioned. And first we are going to design a V-beam electrothermal actuator. Okay, so step by step all the details are mentioned. So as I said, when we open the software, there will be an option to choose the first one, new, and we have to click on the model wizard. Okay, once we click on the model wizard, like this, we'll be getting an option to choose different. One second. We'll be getting an option like this 2D. Okay, so we have to click on this. So it will be giving you the different options. Okay, so if you refer to this one, you will be able to say once you click on the model wizard, then click on 2D button. So it will open the new window. In the new window, it will be asking you to choose the physics, what kind of physics you want. Okay, so already I mentioned for electrothermal actuator, the basic principle of working is Joule heating and thermal expansion physics. So Joule heating and thermal expansion physics will be visible uh, under the structural mechanics. Once you install the software, there will be different set of physics will be there. That's why it is called multi-physics. So you can do with different physics. Here, the electrothermal actuator, which is our interest of work, the which is falling under this structural mechanics. Okay, under the structural mechanics, there is a thermal structure interaction physics is there. From that, we can choose Joule heating and thermal expansion physics. The steps are clearly mentioned in the document. So once you open the software, the 2D we have to take, and from the 2D it will be asking you to choose the required physics. So once we understand that what is the physics behind our design, accordingly we have to choose the physics. Here, electrothermal actuator we are going to design. So the working principle of an electrothermal actuator is Joule heating and thermal expansion physics. Here in COMSOL multiphysics, this Joule heating and thermal expansion physics is available under structural mechanics, under thermal structure and interaction. So I am going to choose that. Okay, so double click on that. It will be getting added to your file. So it is getting added. So once the first step is completed, we have chosen a new file, and it will be asking you to define the physics. Physics is defined. Now we have to choose what kind of study we have to implement. Okay, so study means analysis. Okay, what kind of whether it is a continuous voltage or a stepwise or different types of input can be given. Okay, for example, I'm going to give continuous voltage supply. Okay, so for that, it will be asking you to decide the study. So study can be a stationary study or time dependent study. Okay, so I prefer to do here the stationary study. Stationary study means suppose I want to give a voltage supply. So if I choose stationary study, it will indicate that continuously I am giving the potential. Okay, so if you want a stepwise potential means you can define the time dependent. So with some variables we will be able to give the time defined potentials, like initially 0 volt, then 5 volt, then again 0 volt, like that stepwise kind of, or different values of potential can be given. So here we prefer to use the stationary study. So click on done. So now we added both physics as well as study to the file. So it is getting added. Once both study and physics are defined, it will be coming to a new window like this. initially we have defined as the component or the structure as a 2D design, means two-dimensional design. That's why we are getting a graph like structure like this. Okay, in X and Y axis we will be getting. If we are choosing a 3 dimension, then we will be getting X, Y, Z 3D plane. In the beginning, let us do with the only 2D. Then later we can convert that into 3 dimension also. So here, first one we have to change is the length unit. Okay, by default it will be in meter will be the dimension. It will be mentioned, but we prefer MEMS devices in few micrometers or in millimeter range. So I would like to change the unit of length as micrometer. So that will be mentioned in here, length of the unit. So you can see that in the graph also, the dimension or the unit got changed. Okay, so that is our uh, third step here. Okay, so initially, what model we are doing, that 2D we have chosen. Then what kind of physics to be added, that also we have done. The next one, what kind of study we have to do, the stationary study also we have chosen. Then what kind of length unit we preferred. So in the MEMS, micro electromechanical systems, we prefer uh, this kind of micrometers. So I have chosen the unit as micrometer. So these are the initial steps we have to follow. The same things are mentioned in the document also. So our aim is to generate a structure like this. Now the we have the plane graph is here. Okay, here we have to define our structure. So how can we define that particular V-beam structure here? That is what I am going to mention here. Okay, so here there are different options will be there. First one is creating the geometry. Okay, so if you right click on this geometry, there are different options will be there. Okay, in the pop-up window, you'll be able to see you can draw a circle, ellipse, rectangle, square, or any other structure. Okay, so depends upon our design structure, we have to choose the uh, shape. Okay, here I need a rectangle first because I need the anchors. Okay, in the V-beam actuator, I have multiple rectangles where uh, we have to define how much length and how much width is required for each beam. Okay, so here I need the first anchor, the voltage node or a ground node. I can define the according to the uh, dimension. I'm going to give the length and width as 100, and then we have to click on the build selected. Okay, so here width and height is mentioned here. There we have to enter the dimensions required for our structure. Okay, so our V-beam is having two anchors like this. Okay, one will anchor will be used as a voltage node, another anchor will be used as ground node. So how to define this one? Okay, so for that I have chosen the first one as a rectangle by right click on the geometry. Okay, so from the geometry I will be choosing rectangle, and I'll be mentioning the size of that rectangle as 100 micrometer and 100 micrometer. Okay, so you can even consider a square also. If a rectangle means it can be with a different length and width. So for here I am considering with the same length and width. It can be a square also. And this position indicates at what point it will be started. Okay, so the origin will be like this. Okay, so from the X and Y axis where it will be starting the dimension. Okay, so once I have given the uh, width and length of the required rectangle size and where it is situated, or where it is placed, that also we can mention here. So initially I am keeping it as 0, 0. So once I click on the build, I will be getting a new structure like this. That means one rectangle is drawn here. Okay, so then next step, if we can see that the position we can adjust. Okay, I want from the origin, I want around minus 100 micrometer away from the origin in the x direction. So that I can mention in the same point itself. Here in the position, I am going to mention it as minus 100. That indicates that from here, from the origin, 0, point, this particular point will move back minus 100 points in the x direction. You can see that this is x, so it will go in the negative x direction. So once again click on the build, it will be moving that way. So you can see now the position got changed. Now it is minus 100 and 0. These are the x and y value of this particular point here. Okay, so that is depends upon the designer. We can choose what position and all we have to keep. Okay, and here we can see a few more things here, like rotation angle. Sometimes we have to give some inclination to some of the beams. Okay, then we can define what inclination, how much degree of inclination is required for that particular beam. That can be defined here. Here, since it is a fixed anchor, I don't need any kind of a inclination, so I'm just keeping it like that. Now I need some extra parallel beams here to make the P-beam structure. So again, go to the geometry, click on the rectangle. The required dimension we can mention here. Okay, so in the document I have mentioned how much dimension is required. So it is some predefined values. So depends upon your requirement, you can adjust the values. Okay, I am giving the dimension as 495 and 20 as x and width and height, and inclination of angle 5. So I'm just keeping here 495, 20, and angle of 5. Position I have to verify. So here position will be the same. So you can see that here one beam got placed here. So little bit adjustment we have to make here in order to visualize this point. I am just zoom this point using this zoom angle. I can zoom this point. Okay, so some adjustment in the position I can make, like -1 to make it little more inward direction. So it got up, and y value also I can adjust a little to make this point a little up. So now if you visualize, you will be able to see a fixed anchor here and one inclined beam here. Okay, so as per the V-beam actuator shape, we have two parallel beam here. So we can keep a copy of our bottom beam as a top beam. So in order to do that, we can copy the same. So for that purpose, copy option is available under geometry. So you have to click on the transforms. Okay, if you right click on the geometry, there is a transform options are there. Under the transform option, click on the copy. Okay, and it will ask you which object to be copied. So that object you can uh, click like this. If you bring your mouse over that pointer over the particular element to be selected or to be copied, click on that. Okay, so you can see that that particular element got selected. R2 is nothing but our second rectangle which we defined. So this is our first rectangle, this is our second rectangle. So that we defined here. and there is an option called keep input object. Okay, while copying, if the first object to be copied and maintained there, then you can put the tick mark there. If you want to just copy and delete the first one, then you can put the untick. Okay, so I need parallelly both the beams, so I'm keeping the same. Okay, and here we have to specifically mention how much displacement from the previous to be there. So that is the displacement vector. Okay, from the initial input object, how much displacement should be there. So in the document, I mentioned the displacement as around 40. Okay, I need above 40 micrometer. So in the y direction, in the upper direction only I need. So I think you got the idea like this. So now I copied both the beams here. First beam is here, second beam is here. Since the keep input object is put tick mark here, that's why both are available. If this is not there and if I am building, the previous one will get unselected. So I need both at a time. So I got both beams here. Now we are defining a symmetric actuator. We know that V-beam actuator is an example of a symmetric actuator. So with respect to the origin, both the sides should be similar. Okay. So I can keep the mirror image of this one, this part, whatever the anchor and parallel beams are there, I can make a mirror of that. Okay, that is our next step, which is mentioned in the document. So that is the mirror option. Okay, so in the mirror option means whatever the uh, component elements are available in the left side, same thing can be mirrored in the right side also. Okay, so for that I am going to choose the mirror option, that also available by right clicking on the geometry. You have to go to the transform and there is an option called mirror. Previously we used to copy, now we are going to use the mirror option. Okay, then again it will ask you what are the input objects are there to be considered under the mirror option. So I need the mirror of this fixed anchor and these beams also. And also I need to keep the input objects. I need both sides symmetric. So I will put the tick mark here. Okay. So these are the initial setup for uh, mirror. Okay, and how much far it should be getting mirrored, that also we have to verify. So for that, look, we have to mention the position. Okay, I'm keeping the x field as 500, y field in the same. Okay, so I'm keeping around 500 micrometer in the x direction displacement. Point of deflection only I am mentioning. Okay, and this normal vector to line of reflection means in what way it should be reflected, whether it is in the with respect to the x-axis it should be flipped, or with respect to the y-axis it should be flipped. Okay, for us it should come in the opposite direction. So in the x direction it should get flipped. So I am giving x as -1, y as 0. So the mirror is very easy. Whatever the object to be considered, that input object we have to keep. And if the input object to be kept as such, then we have to put the tick mark. Then how much displacement how to be mentioned in the x and y direction, that we can mention. And the flipping is with respect to x-axis or y-axis, positive or negative. That also we can mention with respect to this normal vector to line of reflection option. And finally, click on the build selected. So now if you see, you can see that symmetrically you got both the structure, both the side you got two anchors and parallel beams. Okay, now we need a central point where it can connect both the uh, parts together. Okay, for that also we can use one rectangle. Okay, so in the geometry, we can select another rectangle, okay, with a dimension of width 30 and 100. Okay, so I'm going to choose that. In the geometry, go to the rectangle. I'm giving the width as 30 and 100. And position, we have to be careful. After doing a few simulations, you will be able to understand that how to give the position properly. So with some imagination, we will be able to define these values. So I already defined it as 485 in X direction and 50 in Y direction. So just enter those values, 485 and 50. So now you understood that both the side got interconnected using a central beam. Okay, so these are the major uh, components or elements in the geometry of our V-beam actuator. Okay, so now we want to consider it as a single element. Okay, as a single device, we have to define it. So here and all, we can see that it is inserted here, like that. We can see. So in order to overcome that and in order to visualize the entire structure as a single device, we can make a union of each component. For that also, you can go to the geometry and go to the Boolean and partitions. Like one option is there above your transforms. Okay, Boolean and partitions will give you the different uh, operations like union, intersection, difference, like that different operations can be implemented. Here I need a union of all the elements to make it as a single structure. So it will again ask you the input object to consider under union operation. So I need all the elements. So one by one you can choose by clicking on each uh, rectangles and anchors. Okay, so I have chosen all the things and it will ask you keep the input object or keep interior boundaries. Interior boundaries means like this. Okay, internally you can see some kind of a lines there. Okay, but as a complete object, I don't need that interior boundaries. It will not look nice. So I'm putting it as untick. Now just to build and see the difference. Now you can see all these points as an intersection here. Once I build it, you can see it as a single element. Okay, now it is a single element. It's with a single click, you can choose the entire element. Previously, it was one by one, individually it was there. Now as a single element, we have uh, developed the structure, V-beam structure. This is the steps we have to follow for designing or drawing a V-beam actuator. Am I clear so far? If there is any doubt, please put it in the chat box. Any steps to be explained again? Handouts are not received. Ma'am, you can share the handout also with the group, I hope. Otherwise, I will share.
I have shared, ma'am.
Okay, okay, ma'am. Yeah, now it is audible, ma'am.
Okay.
One Word document, ma'am, already shared in our group. Confused in positioning the rectangles. Okay, I will see that. That is positioning will be initially it will be little bit confusing, but little with some 3D imagination or some kind of a graphical imagination will be able to place that. Okay, so some imagination is required for that, where we have to start from the origin, how much distance it will move left and right, like that we have to imagine a little bit. Then accordingly the position values you will be able to place. Some trial and error initially it is required. I also define these values after trying multiple times. So Initially, it will be a little bit confusing, but if you try 2-3 times, you'll be able to analyze that after keeping X value as positive or negative, how much displacement will happen. Any other thing? Okay. Shall we proceed to the next step? So far, we discussed only the geometry implementation. So I think geometry is clear to all of you. Now we have to apply the material to the geometry. Okay, now we have a V-beam structure is here, and what kind of material to be applied on this V-beam. Okay, so usually with the help of IC Bangalore, we are going to use soy mumps process for our device fabrication. So in soy mumps, it is silicon on insulator. So silicon material is usually used for the implementation of our devices. Okay, for my device also, previously I have used soy wafer only. So I have to apply silicon into this structure. Okay, the material I have to apply silicon. So there are different types of materials are there. Okay, for simulation purpose, I can define any material. Okay, to analysis purpose, I can take any material. Only thing, the material property we have to define properly. Okay, so material property, either we can refer multiple research papers. In each paper, they will be defining, okay, what is the electrical conductivity, or what is the thermal expansion coefficient, or what is the Young's modulus to be followed. Like that, different material property will be mentioned, so that we can refer, or we can ask some fabrication experienced people, like what kind of material properties we are using. So here software is giving you an option to add the material. Okay, so next step is to add the material to the structure which we are designing. Okay, so there is a library of materials available in the COMSOL multiphysics. So click on the material. In the center, we can see one material option, and click on the add material. Okay, then another window will get pop up here. Okay, so there different material libraries we will be able to see. As I mentioned, this is a multi-physics, so different devices will be able to define or designed using COMSOL multi-physics. Okay, here all of us are under MEMS device, so I'm going to choose a material from MEMS library. Okay, so in under the add material option, there are different libraries are there, but if you choose MEMS library, click on that, and under the MEMS, we prefer the semiconductors, because we are going to process with the soy mumps. Okay, soy mumps wafer only we will be using. So we have to go to the semiconductor. Under the semiconductor, we have to choose the silicon. Okay, so I think the steps are clear. We have to click on the add material. In the add material, different libraries will get open. We have to go for the MEMS library. Under the MEMS library, go to the semiconductor, and under the semiconductor, we can choose the silicon. Okay, so in the silicon itself, various types of silicons are available: isotropic or anisotropic or polycrystalline. Like the different silicon materials are available. But in uh, uh, fabrication process, preferably we'll be using with the single crystal isotropic silicon. Okay, so if there is any variation, means from the fab lab, they will be giving us the instruction. Okay, this is the wafer we are going to use, or sometimes we can have the polymumps process also. Polymumps means we'll be using the polycrystalline silicon. Okay, so there will be some response difference when we are choosing this kind of material. Okay, so for our design, let us choose silicon single crystal isotropic. Okay, so this is the material I am choosing here. So after selecting it, double click on that, then automatically the material will get added to our file library. Okay, so now you can see that the silicon got added under the material. Previously it was blank. Now we can see it is a silicon is here. So for better view, I will close this extra windows. Okay. Now you can see one undo mark here. That means some of the material properties are not defined. That we have to enter from our own uh, research. Okay, like in the silicon, the basic properties, some of the values by default the software itself will give. Okay, and if you need some modification with respect to our material, means you can edit it here. Okay, we can, whatever the value we want to change, we can edit it. Both all the values are editable thing only. So here, if you click on the silicon, the electrical conductivity of the silicon is missing here. So remaining all are already defined by the software, but electrical conductivity is not defined by the software. So we have to research and or we have to analyze and keep the appropriate value here. Okay, so from my analysis, I found some of the material properties. Okay, for the silicon, the electrical conductivity is around 1.45 uh, millisiemens. Okay, so that value we can copy and place it there. Okay, so I'm just copying that value here. And we can enter 1.4, sorry, 45 e to the power minus 3. Okay, so that is the value. So now you can see that that also became tick. That means electrical conductivity value we entered properly. That's why it is accepted that material value. Okay, so sometimes if we are choosing polysilicon, the electrical conductivity will be different. It is 0.25 e to the power of 4. So electrical conductivity of pure silicon and polysilicon are different because of its atomic structure and all. So the basic physics you know about what is polysilicon and silicon. So in the intrinsic silicon, the electrical conductivity is a small value like this, but in polysilicon, the electrical conductivity is like this, 0.25 e to the power 4. Okay, so at present, we are interested to use only the silicon. Okay, so I define the values like that. And if there is any other value changes is required, we can enter those values. At present, I am not going to change any of the values. So material got added as a silicon and all the values are defined. So that is our next step after the geometry. Okay, so next step is we have to define the necessary physics to the geometry. Now, first we develop the geometry, then we define the necessary materials to the geometry. The last one is we have to apply the necessary physics to the geometry. Okay, so from the beginning, I'm telling for the electrothermal actuator, the working principle is Joule heating and thermal expansion physics. So in Joule heating and thermal expansion physics, once we add to the file, you'll be getting multiple elements like this. There will be, it is a combination of a solid mechanics, heat transfer, electric currents, multiphysics, like that. All the kind of physics will be added under the same category. Okay, once we add the Joule heating and thermal expansion physics, we'll be getting the subcategory like this. Okay, so electrothermal actuator should have some electric potential and also it will have some thermal expansion or heat transfer property. So those physics we can define with the help of these subcategory physics. Okay, first let us see about the solid mechanics. Solid mechanics means we have to define what are the points or what are the parts are considered as fixed constraint. Okay, so I already mentioned that only the anchors will be considered as fixed. Remaining all structure, all the beam structure is considered as a suspended structure. Okay, so under that there will be a trench in the beam. Okay, so in the trench, the V-beam will be able to move up and down, depends upon the thermal expansion. For that, we have to keep only the anchors as a fixed constraint. So that fixed constraint we can define here. Okay, so in the solid mechanics, put a just click on the right click. There is an option called fixed constraint. Okay, so click on the fixed constraint. Then it will ask you what are the points to be considered as fixed one. So there will be a manual options will be there, or all boundaries by default we select. All the boundaries will become fixed. But we don't need all the boundaries to be fixed because we need the free movement of the parallel beams. So I am making it as manual. Okay, so these things should be deleted. Unnecessarily, I have chosen this. We can multiple way we can choose this one. Unnecessary. Okay, now so far no boundaries are fixed. So I need a particular boundaries. Like for example, I need this boundary and this boundary to be fixed. Okay, so by default, this entire rectangle area will become fixed at this point. Okay, so you can mention like that, or multiple points to be fixed means you can individually choose each one. For time being, I am choosing only the last two boundaries as a fixed one. Now, in under the solid mechanics, another thing we have to define is the fixed constraint is done. Okay. Here you can define the remaining things. So fixed constraint under the solid mechanics is done. So what are the points to be fixed? You can define only the anchor part I am defining. Next, we have to go to the next physics part, that is heat transfer. So how the heat transfer should happen in the device. Okay, that we can define with the help of this physics. For that, first one is the temperature. Okay, so in the temperature terminal, wherever we are going to define our fixed constraints, or where we are going to define our potential, the same point we have to be protected with the temperature. We have to maintain the room temperature 293 Kelvin at that particular point. So with this temperature definition, that is meant. Okay, wherever we are defining the going to define the potential and the ground node, where we have to maintain the room temperature. Okay, so I am defining the temperature like that. Another one under this heat transfer is heat flux. Okay, heat flux means I already mentioned that it is electrothermal expansion. Okay, so due to the current flow, there will be a thermal expansion. That means the heat has to get propagated, or a convective way heat has to be transferred from one point to another point of the device. Then only we will have the actual thermal expansion. So the heat flux has to move through the device. For that, all the suspended structure should have the protection from the heat flux. Okay, so it will make sure that the device uniformly will get thermal expansion. So I'm choosing the entire boundaries except where I have defined the temperature. So that is one major difference here. So all the boundaries I'll be choosing except the boundaries where I define previous temperature, or where I am going to define the voltage and ground node. So remaining all part should have the thermal expansion. And in the heat flux, few more values we have to define. So that is, we have to choose convective heat flux. Okay, because in the thermal expansion will happen in this convective mode only. Okay, so for that, we have to define this convective heat flux. Okay, and by the general convective heat flux coefficient will be values will start from 5. Okay, in the normal temperature, in the room temperature, the heat transfer coefficient is 5 for silicon. Okay, so I'm defining that value as 5. So these are the two things we have to define under the heat transfer physics. First one is temperature. Temperature we defined only at the point where it is fixed, as well as where we are going to define the voltage and ground node. Second one is the heat flux. Heat flux is defined to the entire parts of the structure where we are expecting the thermal expansion. Okay, so we just kept all those two things. And the next one is the major thing. There we have to define the electricity. Okay, so we need the flow of current. In order to have the flow of current, there will be a potential difference. Whenever there is a potential difference, there will be a flow of current. So in order to showcase that flow of current, I have to define the electric potential. Okay, so I will create one electric potential. So here it will be asking you the place where the electric potential to be applied. So here I am going to give some value, like for example 5 volt. Okay, so 5 volt, 10 volt, 15, like any value you can give there with respect to our design concept. So for example, I am giving it as, I am going to test the device with the 5 volt power supply. So in order to have the potential difference, one side we define the electric potential. Obviously, opposite side we have to define with the ground. Then only the potential difference as well as the current flow will happen. So ground, where we have to define in the opposite side. So ground also we defined. So these are the major parameters we have to define under the physics category. Okay, so here electric potential and ground also defined. So major physics also we added. Now we have to analyze the simulation part. So in order to analyze the simulation part, we have to define some mesh. Okay, mesh means we know that the simulations are some kind of mathematical operations. Okay, so this meshing will help us to make sure that the physics which we are applying to the structure is getting applied on entire uh, design part. Okay, so we can have different size of mesh. Okay, so it can be a physics controlled mesh or user controlled mesh. Physics controlled mesh means by default some mesh dimensions are mentioned in the software, and based on the structure, it will give you some meshing. Okay, I will show you. This is the meshing. If you click on the build, it will show you the. So here you can see that there are some areas where the meshing points are not defined. Okay, it is a normal mesh. So if I go for a little more finer mesh, it will give you a little more better analysis. Okay, but this still here also some parts are not defined properly. So I will go for the extremely fine mesh. So that will make sure that each and every part of the uh, uh, device is covered. Okay, so still there are some points are there, but almost all the points are covered. Okay, if the designer is not satisfied with the extremely fine mesh, then they can prefer the user controlled mesh. Okay, so this kind of user controlled mesh we will be going when we have more complicated structure, like each and every point in the structure to be considered. At that time, we will be choosing user control mesh. That will take little more time, But at present, we need only physics controlled mesh and extremely fine element size. If we choose, most of our criteria will be satisfied. Okay, so that is the last step in the mesh. Okay, so mesh also added to the structure. Now, in the beginning, the type of study which we chosen was stationary. I told stationary means continuously that potential which we applied here is the 5 volt. 5 volt will be provided. Okay, so we have to mention that 5 volt already given that. Now we have to start our simulation. Okay, so this many setup if we done, then you can right click on the study and you can click on the compute. Okay, that will start our simulation. For the time being, I'm just clicking that compute. So it will go to the simulation mode and it will be running the simulation, and after some time it will give you the result. Just wait for that. You can see the progress of simulation here. Few seconds or few minutes depends upon our device complexity it will be taking. Now you can see the simulated structure here. I hope it is visible now. Okay, so once the simulation is completed, under the result, various analysis options will be opened. Okay, so this is the first one is the stress. Okay, so stress means how much thermal expansion stress is generated. So due to that stress, how much thermal expansion displacement happened, like that it is showing. Okay, if you want to see the temperature distribution across the component, then you can click on this temperature. Okay, the heat distribution it will show. Okay, so the maximum heat is distributed in the center part. Okay, so the heat flux we applied in the entire area except this fixed constraint. So there the heat will be in very low heat, but remaining part heat will be very high. So that is this point is showing. Okay, graph is showing like then a distribution of the electrical potential. Electric potential which we here we applied 5 volt. Here it is in the ground node. So that distribution also showing here. We can analyze the electric potential distribution across the device like this. 5 volt is here. So 5 volt is represented with the dark red color. Okay, ground is in the dark blue color. So zero potential is here. So the current will be flowing from this positive to negative. So that also we can see here. The electric field distribution also will be showing like this. Okay, so these are the major analysis we will be getting from the physics. How much is the stress? How much is the temperature? How much electric potential distribution is happening? Okay, so these are the major things. But fundamentally, what we need is we are expecting some kind of a thermal expansion or some kind of a output displacement. So we should know from the original structure how much displacement happened. Okay, so whether it is a 5 micrometer displacement or a 10 micrometer displacement that we want to measure here. To measure that, initially we have to give one point in the physics. Okay, so that I will show you here. So there is under the component, okay, that before starting the simulation also we can give that. Okay, but uh, in order to feel that continuity, I didn't mention in the beginning. So now I am going to define that. Okay, that means we have to make sure that this particular tip only having the maximum displacement. So we have to define a marker here. Okay, a particular point we will mark here and we will measure how much that particular point has moved upward. Okay, in order to select that particular mark, there is an option called definition. Okay, under the component there is an option called definition. We have to define that. Okay, so for that you have to go to the non-local couplings. One option will be there. Okay, So, and from the definition, go to the non-local couplings, and here is an option called maximum. Okay, how much maximum displacement happened to that particular border or a particular point. So I'm choosing that, and it will be asking you which point to be selected. Okay, so I can select with the domain wise or boundary wise or point wise, anything. If I need to mention a particular point, I'll be choosing the geometry entry level as point. I need a boundary because I maximum displacement is happened through this central part. So I will choose this boundary as my area of interest where I want to measure the maximum displacement. Okay, so the operator name by default, the software will give you as max op1. Okay, so this is one setup we have to do. Either you can do it initially itself, or after defining all the setup, you can define this one. So I define now to analyze the displacement. So once again, I will simulate it. I'm going to click on the compute. Then it will give you the displacement wise also a graph. Will show you that. So this here it is completed the simulation. Now for getting the displacement in as a graph, you have to click on the result, and there is an option called 1D plot. Okay, these steps also I mentioned in the handout. You can see that. So once we right click on result and choose the 1D plot, okay, we will be getting a graph. Okay, here in the 1D plot, choose one option called global. Okay, so another window will come here under the global. Here we have to give the operator name. Okay, operator name is what is the maximum operator name is here. Here in bracket it is written as max op1. Okay, and we understood that in the upward direction only the movement happened. Okay, so we can in software it is defined as upward direction is y direction. Y direction will be represented as small letter v. If it is u direction, means x direction, means we have to represent it as small letter u. Okay, so I need the displacement of that central part in y direction. So I am going to plot it. I have given the max OP in bracket v. Why I am giving v means I need the y direction displacement only. Okay, so click on plot. Then you will be able to see there is a small point here. Okay, one blue point you will be able to see here. Okay, so if you click on that, it will be highlighted and it will be showing you how much displacement happened for that particular boundary. So it is showing in y direction, it is almost 4.08 into 10 to the power minus 7. Okay, almost for 0.4 micrometer kind of displacement happened. Okay, with 5-volt displacement for a silicon electrothermal actuator. Okay, so this way we can analyze the uh, uh, structure which we designed. Okay, so that is one way of analysis of V-beam actuator displacement, and other things are like how much stress, temperature, all those things also we can define. Any other doubt? I'll go through the chat once. Ma'am, if before inserting the mirror, if we insert the central rectangle with half width, that is 15 micrometer, and then introduce the mirror, whether that impact simulation? No, the overall our intention is to develop a V-beam actuator. So the geometry can be of any type. If you are comfortable with the drawing the central beam also in the beginning itself, then making it as a mirror, it will work. Okay, so that dimension and all here and there, it may differ. Instead of 30 micrometer, you will be giving 15 micrometer. Finally, we are making a union of all the individual elements. So I think overall effect will be the same. But with respect to the dimension, there will be some variation. I hope I answered Avik Ghosh. Next one. Ma'am, I got this error. I missed some, failed to find the solution, maximum number of newton. Okay, this kind of error sometimes will come with respect to our RAM size. Okay, so this software need a minimum 8 GB of RAM. Okay, and maybe that is one reason. If you followed all the steps similar to this, and if enough memory is there, you'll be able to get the proper result. Yes. I'm not able to add material properties. Okay, I will explain that. Oscillating voltage means that instead of constant voltage, we can give step kind of thing. That time dependent, we can give the voltage. So based on that, in a instead of getting as a constant displacement, we will be getting the fluctuating displacement. Like it will go up and down like that. It will take. That kind of simulation will take more simulation time and memory. It may take some hours also, depends upon our uh, device structure. That's why I'm not demonstrating that. It will take more time for the simulation. The similar kind of response we'll be getting, but only thing up means like a video, we will be getting the response. How to use moving mesh. Moving mesh I haven't used. I used both physics controlled mesh and user controlled mesh. Under user controlled mesh, we can define the dimension of the uh, that element. That is a major difference here. The minimum size which we used in the dimension, like if we have a element size of 5 micrometer or 1 micrometer, so the mesh size we can keep less than that. So we can make sure that even our minimum size component also meshed with our physics. How to give pulsating volt? Okay, I will just show that, but it is time consuming. I may not be able to demonstrate that simulation here, but I can just show that. Any specific reason is there to choose heat coefficient as 5? Because that this is not directly heat, not, it is not similar to our thermal expansion coefficient. It is heat convective coefficient. Okay, because heat convective coefficient means it is the value with respect to that the how the heat is getting transferred from one point to another point. Okay, so for a silicon from 5 to 50 like that, one range of value is given here. So at room temperature, since we are considering our device working in the room temperature, the minimum value by default they are giving it as 5. That's why I have chosen from some research paper, I have chosen the value as 5. Okay, on dynamic input, I will just show. And one person asked about the material properties, unable to add the material property. Material property is very simple. Only thing we have to click on the material and there will be the add material library will be coming. Click on the add material. So here we have to choose the library. For our structure, we are using MEMS library. Under the MEMS, go to the semiconductor and click on the silicon single crystal isotropic. Then once we double click on that, it will be getting added under that. Okay. And by default, some of the values may not be defined. So what value is missing? That particular value we have to define. So for that, you can refer some previous paper or some uh, from the experience of fabrication and some materials, we'll be getting those values. So this is the way we have to define the material properties. I hope I have answered that. Okay, coming to the what is that? Study, stationary study or time dependent study. Okay, here itself I will show you that either we can have the stationary study or time dependent study. That study will be added from here. In the new file, I will show you that. Model wizard 2D. Go to the study and you choose the time dependent study. Okay. So if you want to save the previous file, we can save the file with the appropriate name. VB actuator demo, like that I'm just saving. And it will be giving you the new file with the time dependent. So the initial steps and all will be same. Okay, you have to draw the geometry. You have to keep the unit as micrometer preferably. Okay, and all the geometry will be drawing with respect to our dimension requirement, materials, physics, all those things will be adding. Then here one second. Here this electric potential, and here we are going to define it as a time dependent. So instead of giving this fixed voltage here, we will be able to give some uh, parameter values. So for that we have to define those parameters. Parametric sweep option will be there. Mm. I got confused in that point. Parametric sweep, one option will be there. So there we will be able to define the values like 0 volt, 3 volt, 5 volt, again 3 volt, 0 volt, like that. That sine wave kind of thing, we will be able to provide the values. So at present, I'm not able to find that. I'll be updating that in the document. Okay. At present, I don't have that values with me. Material got added but not showing material properties. So once again, I will show that how to add the material. If you double click on that, automatically the material will be getting added here, and just expand that material. It will be showing you the material properties here. So here, what are the values to be added? You can choose that. Why it is not getting added? I'm not, because if you install the software properly with all material libraries, it should be coming by default. Please make sure that you install the software with all material libraries, all physics, all materials, everything you have to keep tick mark. Then only by default everything will be getting added. If this V-beam actuator simulation is clear, means we will proceed with the U-beam actuator. Shall I go to the next type? Symmetric actuator we already implemented. One asymmetric actuator implementation also we will see. Okay. So we have seen symmetric actuator, and the displacement measurement also we have seen. Same way, asymmetric actuator, especially the U-beam actuator, I'm going to explain once here. So the same thing you can see here in the document also. So next one is the U-beam electrothermal actuator. How to draw these geometries in COMSOL multiphysics. I will just show one with the downward movement and another with the upward movement. We will be able to see that. Okay, so let's follow these steps. I'm taking a new file, 2D, and physics from the Joule thermal expansion. We are adding the physics. Steps are same. These are the field component I mentioned earlier, like U mean X, V means Y, W means Z. Then proceeding to the study, I prefer to do with the stationary. Done. Previous one, I'm just deleting that. So we got the window again, similar way. Unit has to be defined with micrometer. We define that. Then let us draw the geometry. Okay, we'll start with the geometry. Same way, just understand what are the geometries to be there. So one rectangle is required, okay, with 100 dimension and the position as -100 and 0. So in a single stretch, you can define all these things for the rectangle. Dimension is 100 by 100. Position is -100 and 0. There is no rotation of angle. So the first one is defined. Then in U-beam, it is in parallel. So I can keep a copy of that. Okay, copy with the wide displacement of -110. So I'm just defining that as a copy. In the transform, copy. Copy, so keep the input object -110. So it will be downward, it will be coming. So you can see that parallelly two anchors have kept because we need the U-beam like this. U-beam only we are preferring. So in the U-beam, what are the remaining things? Another rectangle with a different dimension. Okay. It should have a width of 1000 and a height of 60. I'm going to define that. Width of 1000 and height of 60 micrometer. Position you can define as minus 1.5 and 0. So we defined the first thicker beam we defined. Okay. Now we need the thinner beam or the hot beam rectangle. The dimensions can be of 1006. 1006. These are variable values only. Hence, it depends upon your requirement. We can define the thickness and width. Here, one example I am choosing like this. Minus 1.5 and minus 16. So both the thick beam and thin beam we have defined. Now we need a tip here for combining these two. So let us see the dimension of that combined one. Small rectangle with the width 10 and length 100. 990 minus 16. So again add rectangle 10. $990. So we got the structure like that. Okay, now we need the union of all the things because here and all we can see the internal boundaries. We don't need such kind of things. We need a perfect single structure. Okay, so for that you can go to the Boolean operation, union of the entire structure we need. So select all those things and keep interior boundaries untick and select build. So we got it as a single U-beam actuator. So the geometry is simple. Anchors and beams define, then apply union to the beams. You will be getting a single device like this. So geometry is completed. Now apply the material. Same way, apply material, add material, go to the semiconductor MEMS library, libraries, and silicon. So it will get added here. Now, any missing properties there or not, that into mark we have to define. So what is the missing? Just check here. You can see here, it is electrical conductivity is not mentioned. So it is 1.45 e to the power minus 3. So it got defined like that. Okay. So there is no into mark now. All materials have been defined. Now we have to apply the physics. So geometry completed, material completed. Now physics. Solid mechanics means we have to define the fixed constraint. Okay, which are the boundaries has to be considered under fixed. So these two boundaries I am considering under fixed one. So that is just solid mechanics, physics. Now heat transfer. In heat transfer, we have the temperature value. Temperature where we are going to apply the potential and the ground. There we have to maintain the room temperature 293 Kelvin. So there we will define the temperature boundaries. And we have to apply the heat flux, convective heat flux to be defined. So just a flux type we have to choose as convective heat flux. In the room temperature, the convective heat flux coefficient is 5 for silicon. So I'm defining it as 5. So heat flux also defined. Now the potential we have to define where we are applying the voltage and ground. So here I'm applying ground in the opposite beam. I am applying fixed constraint. I am applying 5 volt. For example, 5 volt I am giving. So the necessary physics also applied. Now we can apply the mesh. So physics controlled mesh or user controlled mesh we can use. User controlled means we have to define the values and all. Okay. So preferably we'll be using with you physics controlled mesh. Extremely fine mesh will be choosing. So all the points have been defined properly. So meshing is perfect. Now, anyway, we need the maximum displacement plot also. So beginning itself, let us define where the maximum displacement to be mentioned. So that we can define from the definition under the component, go to the non-local couplings and choose the maximum. So that boundary we have to choose. So I will be having the tip movement here. So I have chosen that boundary. So after defining all the physics, meshing, and the maximum point, I'm going to compute it. So click on compute. It will do the simulation. Well, let us see the response. The simulation is in process. So you can see that there is a upward deflection in this tip. Okay, so let us see how this is a stress distribution and how much the temperature is getting distributed. So you can see that the thin beam is having the maximum temperature. Okay, thick beam is almost in the cool temperature only comparative to the thin beam. Okay, that's why due to the difference in uh, thermal expansion, the thin beam will have the better expansion compared to the cold beam. So it will be having a upward deflection. Electric potential distribution, because here we have applied the voltage 5 volt. Here it is in the ground node. And let us see how much displacement happened. So for that, click on result, choose 1D plot group. Then in the 1D plot group, right click and choose global. So it will be asking you to give the expression. So expression we have to choose under here. What is the expression? Max OP1. Max OP1 of upward direction means it is again in the y direction. So let us keep bracket small letter v and plot. So it will be giving a value as 2.5375 into 10 to the power minus 7. So almost 0.25 micrometer. It is giving you the dimension of displacement. So these are the two electrothermal actuators basically we are using in various applications. So one is symmetric actuator, V-beam actuator, or asymmetric actuator means U-beam actuator. The dimension and the but overall structure we can change according to our design concept, but the fundamental operations will be like this. Any further clarification requirements, you can put it in the chat box or you can ask me. So any clear procedure for installing software, especially after trial period? The software link which we shared is actually it is a cracked version. Okay, so there is no trial period and all for that. Any further doubt in this? Is the process flow same for 3D? Yes, all the steps are same. Only difference is that the how the dimensions we are defining. Okay, I will show you one 3D also. One second. I'll just save this file. So take the new one, model wizard, choose 3D. Okay, same steps will be same. How we are defining the physics and all, study and all, the same step. Same way define, add, proceed to the study. I'm defining stationary. Now, if you define the unit, now you can see here the window is changed. Previously, it was a 2D graph. Now you can see with the 3 dimension, it is a 3D. So here, if you try to draw the structure, like in previously it was rectangle. 2D means only rectangle, square, circle kind of thing will become. Here it will be in the block or cylinder, sphere. So 3D will be coming. So there you have to define the values like that. Suppose if I need 10, 10, 10 like that. So I'll be getting a block here. So that block you can rotate. Okay. So that is according to our convenience we can define, and the position and everything. Little more higher level of imagination we require here. Okay. So once you're confident with your 2D direction and 2D designs, you can directly go with this 3D. There you can define all the XYZ values and implement it. Or sometimes you can export the values or export the design from 2D to 3D also. So that is depends upon our requirement. We'll be choosing all those things. There will be some export options will be there. If you right click, like export option will be there. So from export from 2D to 3D is possible. So that under we will be taking. Any other doubt? Why I designed only with the 2D structure means if I choose with 3D, the simulation time uh, will be very high. The computational time it will take more, and for demo purpose it may not be convenient. That's why I have designed only with the 2D structure. Same things we can design with 3D also. So if you wish to proceed with the fabrication process and all, it is finally do the simulation with the 3D structure. Simulation time or computational time may be higher, but you will be clearly able to visualize the simulations in the real time, how the your 3D structure will uh, work. Similarly, we will be able to see that. I hope I have clarified all the details regarding the simulation. Any further clarification required? I will mention my mail ID also here. So anybody is having any kind of doubt regarding the simulation, you can approach me through a mail. Unable to see the value. Okay. We can download some values also. I will show you that. You are telling like from the result, if you click on export global, if you show like if you highlight this point, usually the value will be showing like this. If it is not coming, you can copy and see the data also. Copy plot data to a table. One option will be there. So it will be helping us to take the value, or there will be some export option will be there. What are the values required? We can take whatever it is. If you highlight this in a new window also, it will be coming. What is the value? It will be coming like that. We can extract the value or export the value in different way. So what way we need the value, like that it will be coming in a table form or clipboard, or if you need some kind of images, those things also possible. If you want this particular image, that we can choose here. Okay, in a particular point, let us make plot value. And if you go to the particular folder, it will be showing you the graph. So all these things possible. We can note the value like this. From that particular point value, we'll be able to highlight that. Or if you need something in table form, that also it will be showing. Here the maximum value, it will be showing like this. The software link already shared in the document. I think in the group you can see that. It is like a drive link it is given. So you can download, and installation process step also mentioned there. So just click on that and install. Any other doubt? For fabrication purpose, directly from COMSOL we will not be getting, but .stl format we can export the file. Okay. Yes, as Srija madam is telling, fabrication process stuff we'll be discussing in the next session in detail. This is only the simulation part. So you can connect to me through the mail. I will respond. Ma'am, I think I have covered the necessary points.
Okay, Joshita ma'am. If any more questions are there, participants, you can type in the chat window, or you can connect with ma'am also. Just a minute, ma'am.
Yeah, sure.
Thank you, Joshita.
Thank you, ma'am.
Yeah. Any other questions from the participants?
So, Dr. Joshita, you have given a detailed explanation about the hands-on. And all the participants, we will be sharing you the recording of this session. This is also live streamed on the Census Council YouTube channel. So that is also available there. You can go and refer it anytime and have a lots of practice so that when we go for the next session, the knowledge of this will help you out. Thank you, Dr. Joshita. Thank you, everyone. Any doubts are there, you can share it in the group as well.
Thank you, ma'am, for giving me an opportunity.
Yeah, and dear participants, the next session will be fabrication. So you will be receiving email regarding the next session's timing and schedule. Thank you.
Ma'am, you can stop sharing. We'll close it. Yes, thank you.
Yes,
Thank you,
thank
everyone.
you.
Thank you.